All right. So to start off, so today I'm going to tell you about this work on sequential fair allocation. And our motivation was based on this program, Feeding America, which is addressing hunger in America, especially for those who are having low resources and have difficult time getting access to food. And so in particular, we are partnering with a food bank, a local food bank, the Food Bank of the Southern Tier, that provides food to people in the community for free or for low cost. And the particular problem that we're looking at is this program they have called a mobile food pantry. This mobile food pantry program is where they have a truck that they load with food at the beginning of the day. And the truck will have a certain route of different locations it will stop by along the day. So maybe it will stop by at one town at 10 a.m. and then they'll set up shop, and the people will line up, and they will distribute food to people at the first individual location, and then they'll pack up, go to the second location, say a few hours later, and then again set up shop and distribute food, and then pack up and go to the next location. So this mobile food pantry has to make decisions at the beginning of the day of how many like food resources to pack onto the car. And then as it visits these different locations one by one, it has to decide how much food do I distribute to people at location 1 before it gets to see how many people arrive at location 2, location 3. And so in this sense, the allocations are made sequentially, or also we call it online, because you only have to commit to a decision on what to allocate, what to distribute before seeing what comes later. And there's only partial information about the number of people arriving at each distribution location. But what we do assume is that that we have access to historical data. So because the mobile food truck, they perhaps run this route maybe once every week, and so they can collect data over time about to estimate the rough distribution of the number of people arriving at each location, but they don't actually know the exact realization of how many people are arriving at each location. So that's the kind of challenge that we're looking at in terms of how to allocate resource in a sequential online setting. And so to just abstract this to a to formulate the problem in an abstract sense, we will assume that, say you have a certain budget. Let's say the budget here is 5 units of a resource, and at each time there may be 2 different types of agents, the green agent and the yellow agent, and they have different utilities for the or different demands for the budget for the resource. And the decision-making agent needs to decide how much of this budget do I allocate at time 1, and how much do I need to save for the subsequent times. So it can decide, maybe I'll allocate 1 unit of the resource to the agent of type 2, of the yellow type, and then half of a resource to the agent of the green type, and then it only has 3.5 remaining units left of the resource for the second round. Perhaps at the second round, then an agent of type the yellow type arrives, and this will continue where say at each time again you decide how many to allocate, and then you have the remaining budget, and then the next time you see what are the agents that arrive, and you again have to make a decision of what to allocate. And these number of agents of different types we assume is drawn from a distribution. This distribution we assume is known in advance. You can think of approximating this distribution using historical data. And for an agent of say type A that arrives at a particular round T, this utility, we assume to be linear, in that it's just the utility of the agent is linear in the amount of resources it's allocated. And So we may care about some notion of maximizing the agent's utility, subject to the constraint on the fact that you can't ever allocate more than the amount of resources you have. You can't never allocate more than your budget. Okay, I got it. Thanks. All right, so we can ask what is our objective for this allocation? So what is the thing that we really want to optimize? And this will depend on the application. So suppose your allocation setting is that you're allocating airline seats, and now these individuals arriving to compete for the resource are going to be travelers, and you want to decide, travelers that have different utilities and are willing to pay different amounts. When they arrive to your platform, you want to decide whether to allocate the resource to them or not. And you have a fixed budget on how many seats are on this flight. So this is a setting also of sequential allocation, but the goal is to maximize revenue here. Another application might be one where, suppose there is a university shared resource. It could be university supercomputer time. And now the agents are going to be researchers that kind of arrive to the platform that try to, request for some supercompute time. Again, this supercompute time is budgeted, and what the university might care to optimize is some notion of a welfare. But of course, because this is a shared resources, they're not. They may not want to. They may not charge for it. So you want to figure out how do you maximize welfare, but maybe without using money to manage that allocation. In our setting today, we're going to look at a very different kind of objective. So our resource is going to be the mobile pantry stock of the food, and the agents are going to be the individuals that arrive to the soup kitchen queue. And our goal here now, you can ask, what is the right objective here? Here you're not trying to maximize revenue. It's not clear exactly. The right notion of welfare. And here, what our goal will be is to optimize a notion of fairness. So what we want to make sure is that that there's some fairness across agents that show up to the food bank, the mobile pantry. And so fairness has been studied in offline settings quite a bit. So here, think of a one-shot allocation setting where you have, let's say, n agents, you have m items, and the agents have certain values or utilities for these items. And the agent's final utility, again, is linear in the amount of allocation he gets assigned to for each of these items. And we have some budget constraints about how many of each of these items we have. Now, in this setting, there's 3 different ways of people have viewpoints of looking at what does fair mean. So one perspective is taking an algorithmic approach that particularly defines some objective that we can optimize for. And 2 common objectives are what's called a max-min, which would be you want to maximize the minimum utility of any agent. Another objective that we might optimize, and I'll mention this why in a bit, is a notion of a geometric mean of the utilities of the agents. This is also called the Nash social welfare, and it turns out that has very nice properties. So another approach is a kind of economic viewpoint, which is, suppose I just give every agent an equal amount of some fake budget and let them decide amongst themselves. So this might be, so you give every agent an equal amount of budget, and then you allow the agents to do some kind of free trade, and you hope that by this free trade they will end up with some kind of allocation that everyone thinks is fair. And another third approach is to take an axiomatic viewpoint, which is to define a set of properties that we want our allocation to satisfy, and that captures what our notion of what we think fair means. And so there's 2 critical aspects that we might care about for fairness. One is what we call a Pareto efficient. We want an allocation to be Pareto efficient, meaning that any change that you make to the allocation should make someone worse off. So you don't want an allocation which is somehow strictly worse in some sense that you can make a change to it and everyone's happier. So that would not be a good allocation because it's not, everyone will agree that that's not optimal. And the second property you might care about is a notion of envy freeness. So that no one wants someone else's allocation. So this notion of envy, so that the allocation is such that I don't envy anyone else's allocation, meaning the utility I have for my allocation has to be at least as good as the utility I have for anyone else's allocation. And that captures our some notion of this fairness, that I'm just as happy with what I got than what anyone else got. So this kind of shows you there's these three different viewpoints of fairness. And the nice, the kind of very beautiful theory that Varian proved, back in 74, is that in fact, when you have divisible items and you have linear utilities, that these three different perspectives lead to the same outcome. Meaning, if I take if I find the allocation that maximizes this Nash social welfare, which is, again is this geometric mean of the utilities, that will produce an outcome which is also satisfies Pareto efficiency and envy freeness, and also happens to be the outcome that results from this kind of free market. So this is a very beautiful result that kind of shows not, under this setting where divisible items and linear utilities, in fact, we can find a fair allocation that satisfies the properties we want. And furthermore, this Nash social welfare, so this quantity, this geometric mean, when you have linear utilities, solving for the allocation that optimizes this can reduce this to solving a convex program. So typically people will actually solve, maximize for the log of this quantity, which becomes the sum of the log utilities. And that's it's called the Eisenberg-Gale program, and that is a convex program. So the nice thing is that it's algorithmically efficient, but also has all the properties we want. But now the challenge we have is that we're actually in a online sequential setting. So so in this sequential setting, the challenge here is that we actually don't know how to, we have to make a decision of what to allocate before we know the future arrivals. So in that sense, we're not able to solve for this, optimize this Nash social welfare because some of the quantities are not yet revealed. And so it begs the question of, what's the right notion of even defining what's the notion of fairness for a sequential allocation? And there's a couple of different approaches that previous methods have taken. One is to look at looking at some notion of ex ante envy freeness, and think of ex ante to be this notion of before the realization happens. If I just look at in expectation across all sample paths, what is the expected allocation, and how do we look at envy freeness with respect to that expected allocation? Another approach is to get comparative ratio or additive guarantees on this Nash social welfare. Another approach is to look at this max-min style of guarantee, but typically also ex ante. The problem with these kind of guarantees is that these probabilistic guarantees don't end up translating to a notion of ex post fairness. So what I mean by ex post fairness means after the realization, after the demands are realized and the allocation is made, then you can look back in hindsight and ask, oh, what was the allocation I gave actually fair? And so the problem with ex ante is you only look at expected allocation, and an expected allocation can be, can, even if you have free, envy freeness or fairness in terms of the expected allocation, you can still end up with very unfair allocations ex post or in hindsight, because to get expected value of, let's say, allocation of 1, you can either always give 1 unit of the resource, or you can give 10 units of the resource with probability 1/10. And these properties have, well, I mean, these two allocations will have very different properties ex post. So what we're really looking for is some notion of ex post guarantees. And so that's what our work focuses on. And again, so what we do is we provide some results that are, again, motivated by this online fair allocation problem for mobile food pantries. And what we show is that our approach can minimize this notion of additive deviation from the ex post Pareto efficient and MV-free solution. Again, this additive deviation is much stronger than a competitive ratio style guarantee. And we're able to furthermore fully characterize the achievable trade-offs between the Pareto efficiency and MV freeness and show that our results actually gets optimal with respect to those trade-offs. And our algorithm is a very simple policy based on ideas from safe model predictive control. And we do show good empirical performance on mobile food pantry data. And I want to emphasize here that having guarantees on both the Pareto efficiency and MV freeness is important because if you only focus on one or the other, they're easy to satisfy in isolation. So if I just wanted to satisfy Pareto efficiency, I could just give everything to, distribute everything at the first location. And then and that would be Pareto efficient because if I shift any resources away from the first location, the people there, the individuals there will be strictly worse off in utility. And so again, it satisfies this notion of Pareto efficiency, but it's clearly not MV free because then the latter locations have nothing. If I want to just satisfy MV freeness, I could just give everyone nothing. And that would be MV free, but clearly not efficient. And so it's very important that we want to look at the tension between trying to satisfy both Pareto efficiency and MV freeness. So let's start with a simple model where we only are looking at single resource allocation. So here, suppose we have a mobile food pantry that has a budget B. It visits T locations sequentially, and each location will have N sub T people, where this number of people is sampled from a distribution. And this distribution, we allow this distribution to be different for each time, so each location T, but it is something that is known in advance. So think of it as being approximated by historical data. And each person will have we assume has, let's say there's one type, so they have the same linear utility. So this is a very simple case where it has one resource and one type. Now, in this case, we can think about, what's the right notion of sequential fairness here? If we actually knew the number of people arriving in advance, so suppose we knew how many people are arriving in total, then the optimal fair allocation is simply just to take your budget B and to divide it amongst all the individual evenly. And this is because again, we have only one resource and we only have one type of individual. So the clear optimal fair thing to do is just split it evenly. And so the notion of, how do we evaluate the performance ex post of our policy? So suppose our policy allocates Xi to individual I, then how we evaluate how close we are to the best fair solution we can capture with two quantities. One quantity we call delta NV. So this is kind of the distance from the NV-free solution. This is going to be again, maximum across agents of the allocation that the agent received minus the fair allocation that the agent should have received. So this delta NV is saying how much distance away from the, again, NV-free optimal solution. And delta efficiency is going to look at the difference to the Pareto efficient solution. So meaning that thinking of you can also think of delta efficiency to be the amount of waste. So you can think of kind of Pareto efficiency also as capturing this notion that there's no waste in the system because you can't just, there's no unused resource that you could just add to the allocation and make everyone happier, right? So in this case, the efficiency, then the delta efficiency, so how much is away from efficient solution, is captured by the total budget minus the amount that's allocated. And again, you can think of this as the waste in the system. It's the amount that is not allocated. All right, so so this is our setting for the single resource, single type. And maybe I'll pause here. Are there any questions about this simple setup? All right. So next we'll take a look at the, say the formal model, which has a more general setup. In the general setup, a principal is tasked with dividing, say, k different resources over t rounds, and each resource has a different budget, bk. And in every single round, the principal will observe this vector, which is the number of agents of each type that are at that location. And the principal then decides how much to allocate to each type of agent. And the agents get linear utility. And their utility, again, depends on their type, but in a linear sense. So you can think of theta relating to a linear coefficient vector. And the total resource consumption then is going to be the number of individuals of each type times the allocation of each type. And again, you should think of this allocation being it's a vector of length k, meaning it specifies how many of each of the k different types of resources it allocates to the agent of type theta. And so this total resource consumption itself is also a vector indicating how many resources of each type are consumed in this round. And in order to motivate these different types for our setting, you can think of types being something like, say, there's a vegetarian, and the vegetarian clearly has very different utilities for the food than someone who's not vegetarian. Or you can imagine have an individual, a type who has a family that has young kids, maybe a family with infants, then they will clearly have a different preference type because they will have utility for example, baby formula compared to other agents. And so you can think of this type as capturing that the heterogeneity in the needs and demands of the individual showing up at the distribution site. And so in this general setting, when you have multiple resources, multiple types, we can look at the same notion of ex post fairness. And we'll look at these three quantities, which is some notion of envy freeness. So again, we can look at, so envy freeness means that there's every individual has a higher utility for the allocation he himself got. So the utility of agent of type theta for the allocation given to agent of type theta is at least as good as the utility the agent of type theta has for the allocation given to any other agent type theta prime. And proportional means that the utility the agent has for what was given to him has to be at least as good as utility of splitting the resources completely proportionally. And the last property we might care for is this notion of efficiency, Pareto efficiency, meaning that all the resources are consumed. So we don't want any waste. So again, these are properties that you might care about for a notion of ex post fairness. And again, because of the result of Halvarian, you can show that this unique allocation, which we will call X opt, it can be found by maximizing this national social welfare or its logarithm, which is called this Eisenberg-Gale program. So the Eisenberg-Gale program is maximizing the sum of the log utilities. And again, this is relating to the setting where if I knew all the number of individuals arriving of each type in advance, then I would just solve this program. And the nice thing is that the allocation that solves this program gives me these three properties: envy freeness, proportionality, and efficiency. But of course, in a sequential setting, we can't actually solve for this optimal objective. And so we want to take, another issue is that even if you try to solve for this, optimize for this objective function, There's no guarantee that an approximate solution to the national social welfare is going to be approximately fair in any way. So we're really going to look at what would lead to an approximately fair solution. And so in our online setting, what we'll look for is an allocation which has low delta NV, so this distance to NV free, which again is defined as the maximum overall rounds and overall types of the utility, the difference between the utility the agent has for the allocation he was given minus the utility the agent would have gotten from the hindsight optimal allocation, this X-opt. Again, recall X-opt is the solution to this Eisenberg-Yale program. And the second quantity we care about is this distance to Pareto efficiency. That's delta efficiency, which is going to be the amount of resources that are wasted. So it's the sum across all resources of the budget we have for that resource minus the amount of that resource that was allocated. So this simply just generalized to the multi-type setting. All right, so the intuition for these two quantities is that this delta NV, you want this to be small. Oh, okay. Yeah, good question. So someone asked, what is this proportional? This proportional property is that you want that the utility that the agent gets for the allocation that he's given is at least as good as utility he gets for this even allocation of dividing the budget evenly across all individuals. I mean, in the simple setting, the proportionality is already subsumed by NV freeness and efficiency. And so that's why we focus on delta NV and delta efficiency. But the proportionality kind of captures this idea that at least whatever allocation you do, you want to be at least as good as just the resources across everyone. But you can think of let's say if there's only single resource, then evenly dividing the resource among everyone is optimal. It is NV free and efficient. In the general multi-type setting, because there's different utilities, then evenly dividing the resource amongst everyone is probably not going to be efficient or NV free. Okay, so all right, so the intuition, right? So we care about delta efficiency because we want to promise to individuals that they will receive as much utility for their online allocation to what they should have gotten in a fair solution in hindsight. And we care about delta efficiency because we want to make sure the resources are used to limit waste. All right, so this is a summary of the result that we're able to show. We're able to show that, in fact, there is a trade-off between what's achievable in terms of this delta NV and delta efficiency in this online sequential setting. So in particular, first of all, we show that that any algorithm has to suffer this delta NV of at least 1 over t to the 1 over square root t, so t to the minus 1/2, and that's characterized by the left red bar, and that arises from an impossibility result due to statistical uncertainty. And then second, we show a relationship between delta NV and delta efficiency, that any algorithm has to suffer delta NV times delta efficiency that's order 1, meaning that if that they're kind of inversely proportionally related to each other. And that results in that curve that you see that drops as 1 over delta NV. You can see the curve that shows that delta efficiency, the achievable delta efficiency drops as 1 over delta NV. And then on the upper right, we're able to show this green region that we can achieve any point. To any achievable point, we're able to also provide an algorithm, a very simple algorithm called guarded hope that actually achieves any point you want on this Pareto efficient curve. All right, and so the nice thing we also showed is that this algorithm that we're able to prove the results for is actually a very simple algorithm, and we do also show that it performs well in practice and simulation as well. And in simulation, we do verify that this algorithm actually does achieve this inversely proportional relationship between delta NV and delta efficiency. So we'll come back to that later. All right, so let's unpack what the main theorem is. Oh, actually, I should have paused. Are there any questions about the summary of the results first? All right, all right. Then I'll go in and I'll unpack it a little bit more in detail. So let's consider the setting where the budget scales linearly with the expected demand. This can be relaxed a little bit, but we'll just use this for easier notation. So this n is going to be the sum of the number of people who arrive. So again, n is the total demand. So supposing that the budget scales linearly with the demand, then our result shows these three different pieces, which correspond to the three different points that I kind of briefly summarized on the graph earlier on. So the first piece is a statistical uncertainty principle that any online allocation must suffer a delta NV that is at least 1 over root t. The second one is that is this NV efficiency uncertainty principle that any online allocation must suffer this relationship between delta NV and delta efficiency have to be inversely proportional to each other. And the third one is that we achieve this optimal trade-off with our algorithm guarded hope. So for any value of LT, think of it as a parameter, meaning a budget on the amount of delta on the amount of delta NV we're willing to incur. So any choice of LT that's greater than roughly 1 over root t, then our algorithm achieves with high probability, with probably 1 minus delta, achieves this bound of delta NV less than equal to 1 LT, and then this delta efficiency, which is inversely proportional 1 over LT. And so what we'll do for the next part of the talk is focus on giving some intuition of where do these results come from and how do you prove them for the single resource, single type setting. And the results generalize, again, to the multi-resource, multiple type setting. And the intuition and concepts are actually very similar. So you'll get the key concepts by looking at the single resource, single type setting. So again, for the single resource, single type setting, it's a little easier in that the optimal allocation we know is B over N. Again, because N is a random variable, though, think of B over N being a random quantity because of the demand, because of the randomness in the demand. And delta NV is going to be, again, the distance between the allocation and this optimal fair allocation. And delta efficiency, again, is the waste. So the budget minus the amount allocated. So let's first take a look at how do you prove the statistical uncertainty principle? So how do you prove that any online allocation has to suffer at least 1 over root t NV? And this has to do with just the statistical uncertainty in the number, in the demand. So in particular, you think about the very first allocation. This is the very first round. You need to decide and commit to some allocation to individuals in round 1. And so whatever you choose to be that round 1, then your delta NV is going to be at least the distance between what you allocated in round 1 and this optimal allocation B over N. And round 1 is going to be the kind of critical round that governs that results in this negative result, because round 1 is when you have least information. And so how you would show that this delta NV therefore is lower bounded is to show that this quantity n, this demand n, is anti-concentrated via using Berry-Esseen. So Berry-Esseen is a result that says if you have a sum of random variables, it kind of characterizes the convergence to the Gaussian distribution, to a Gaussian-like distribution. In particular, it will give you then, you can use the result then to say that as long as the variance of this distribution is bounded away from 0, then the not only the expected demand constraints within roughly root t of its expectation. It also you can also say that with constant probability, there's it also is away from the mean by order root t as well. So it has to do with this root t anti-concentration that you get this root t 1 over root t delta NV lower bound. And the next thing you want to show is this NV efficiency uncertainty principle. How you show, and again, it kind of shows this fundamental trade-off. And to give an example of the implication of this trade-off, it means that if my delta MV is 1 over root t, then my waist has to be at least root t. And if my delta MV, if I'm allowing it to be a little larger, so if I allow it to be 1 over t to the 1/3, then my waist has to be at least t to the 1/3. Or alternately, I can instead, if I allow a constant delta MV, then I can get constant waist. So how you show this is by first using the fact that if the algorithm needs to satisfy a minimum bound on delta MV, then it has to stay within a certain range of allocations. So recall delta MV is again just the distance from x opt. So in seeing this plot on the bottom, you can see the line for x opt. That would be, supposing you knew the demand, the optimal allocation would be that line. Of course, again, you should remember that this line is it's a random quantity. There's some stochasticity in it due to the stochastic demand. But this delta NV condition means that whatever my algorithm allocates has to stay within below x opt plus LT or above x opt minus LT. So because my delta NV is constrained, then I have to keep my algorithm within these two what I'm going to call guardrails, within these two guardrails. Now, the challenge actually is satisfying the lower guardrail. In particular, so if my algorithm is too aggressive early on, it might accidentally run out of budget, such that at the end of near the end of the latter rounds, it might not have enough budget to satisfy even the minimum guardrail. So in order to make sure that the algorithm has enough to satisfy this minimum guardrail, the algorithm has to be conservative. And that needs to ensure that the remaining budget after each round is enough to guarantee at least x opt minus LT of the optimal allocation in hindsight. But however, now the other aspect is that suppose I get to round the last 1 over LT squared rounds. So think of time t being being capital T minus 1 over LT squared. We need to account for this the fact that in the last rounds, there's some statistical uncertainty in the amount of people are arriving. And on one hand, we need to be conservative to have enough to allocate for this last 1 over LT squared rounds. But then we also cannot give out. So if we end up with too many resources, we also have a limit of how many we're able to allocate each time. We keep the budget to be at least, say, the x opt. So x opt minus LT is the lower guardrail. So it's the minimum that I allocate to each person times the kind of upper confidence of how many people might arrive. So there's a reasonable probability that I get that the number of people that arrive is more than roughly square root t minus the remaining, so the remaining time plus the expected amount. And so that kind of forces my budget to not be too small. However, in the worst case, if the arrivals are close to the lower confidence bound of the number of the demand, so meaning that in the worst case, if too few people arrive, If I wanted to burn off extra resources to have less waste, because of this upper guardrail that is enforced by our condition on the delta NV, we cannot allocate more than X opt plus LT for each of those people. So the difference between the conservative threshold we need to budget and the maximum amount that we could allocate when there's too few people, that difference exactly results in this delta efficiency lower bound of 1 over LT. All right, so that's kind of the explanation for the lower bounds, the impossibility results. I'll just pause here and see if there's any questions. All right. So finally, then I will tell about what's the algorithm that actually achieves this optimal trade-off. So this algorithm we call guarded hope, and given a parameter, this LT is, think of it as your budget on delta NV. We'll first use concentration to generate a pessimistic allocation by replacing this number, this demand in the Eisenberg-Gale program with a high probability upper bound. So in particular, think of, so let me actually unpack that again. Suppose we have, so if we had the if we knew the demand of people that are arriving, we would just plug it in the Eisenberg-Gale program and solve for optimal. But because we don't know the number of people arriving, we're going to plug in an approximation for it. But we want a conservative approximation, meaning that we're going to plug in an upper bound on this number of people that arrives. And so that's one condition that we'll need on our algorithm, is that we'll assume that the distributional information allows you to compute some kind of high probability upper bound on the demand. Now, by solving the Eisenberg-Gale program with a high probability bound on the number of individual, it kind of gives you a very safe allocation. We call this X lower bar, meaning that this is the amount that I want to minimally make sure to save for each individual. And if I allocate by this amount, then I will guarantee that I have enough because it's computed using a upper bound on the demand. So in a single resource type setting, the upper bound on the demand would just be your expected demand plus root T because of the kind of, again, because of standard concentration, you expect your deviation to be on the order of root T. And so this X lower bar is going to be your total budget divided by this upper bound on the demand. So think of it's a budget divided by your expected demand plus root T. And we're going to set this X lower bar is going to be our lower guardrail. Our upper guardrail, X upper bar, is going to be simply the lower guardrail plus this LT, which is again is our buffer on how the deviation, this L delta MB. And a key property that we would need to show is that because of concentration of this, so in the single resource setting, because of concentration of the demand, that with high probability, this X opt, which is B over N, does lie within these two guardrails. And that allows us to guarantee the desired bound on delta NB. In the general multi-resource setting, the one thing that you will need to show is that you need to show concentration of the optimal solution to the Eisenberg-Gale program for general multi-resource setup, which is slightly more complicated, and you need to show essentially some properties, sensitivity properties of the solution to the Eisenberg-Gale program, that if I solve the Eisenberg-Gale program with demands where that are like with different values of the demand, that if the demand is very close, then the solution also ends up being close, and that's kind of one key property you need to show in order to guarantee that that by playing with these upper guardrail and by playing according to the upper guardrail and lower guardrail, the algorithm does indeed satisfy the bound on the delta MV. All right, so we did the first step in order to compute this x upper bar and x lower bar. And again, this x upper bar and lower bar are calculated so that with high probability x opt lies within this this range. And our algorithm is going to try to allocate by according to either the upper guardrail or the lower guardrail. So it's going to try to limit itself to these two guardrails. So one naive allocation would be, well, why not I just always be conservative? I'll always allocate according to the lower threshold x lower bar, and make sure that I never run out of resource and always have enough to allocate according to lower bar. But the problem is that this could be very wasteful because the total waste could end up being t times this difference between x upper bar and x lower bar. So it could be t up to t times LT. And so this does not satisfy this optimal MV uncertainty principle, MV efficiency principle. So the better option is actually to say, well, why don't I allocate according to X bar while ensuring that I have enough upper bar, while ensuring enough resource to ensure allocating to X lower bar to everyone in the future. So let me unpack that. So basically, you want to make sure that you're conservative enough to save enough budget to allocate the lower resource to everyone in the future. But however, if it turns out that the number of people that have arrived so far is somehow less than what you expected, you might end up with a budget. You might end up with a budget that's kind of higher than what you need to allocate to X lower bar to everyone in the future. And in this case, when you have extra budget, then you allow yourself to allocate more aggressively according to this upper threshold. So in particular, that you can exactly state it here, where in round T with remaining budget BT, if your budget is enough to allocate the more aggressive threshold X upper bar to everyone at this time and save enough to allocate X lower bar to a conservative estimate of the demand on everyone in the future. So this conservative demand is going to be, again, an upper confidence bound on the demand. So think of that as expected demand plus order root t, which t minus little t, which is root number of rounds until the end. So if you have enough budget to allocate X upper bar to the people now and X lower bar to a conservative estimate of the people in the future, then you go ahead and allocate this more aggressive upper bound. Otherwise, you allocate conservatively according to the lower threshold. And so in summary, this algorithm is really just that. It's very simple. Again, step one, you calculate these guardrails, the X upper bar and X lower bar. And then given these guardrails, we have a very simple rule that says, if you have enough to allocate, make sure that you always have enough to allocate at least your lower threshold. And then if you have extra, then allocate according to your upper threshold. So this makes sure that it kind of straddles that tension between making sure you don't run out so that you're always able to satisfy this delta NV bound. But also, whenever you have extra, it will allocate more aggressively to try to reduce waste. So again, it gets these two guarantees that we want. One, that it does achieve this bound on the delta NV by the construction of these guardrails and concentration of this X opt. And two, it will achieve this bound on this delta efficiency by arguing that the budget is tight anytime the X lower bar is allocated. So in particular, recall X lower bar is allocated whenever you don't have enough resources to allocate X upper bar at this time and save enough to allocate lower bar for the rest of the time. So anytime you allocate X lower bar, it means that your budget is just about right at the threshold that you need it to be to make sure you have enough to allocate lower bar to everyone in the future. And so it kind of is a tightness on your budget. Make sure that you don't have too much. And furthermore, you can argue that there must be an instance within this last order 1 over LT squared rounds for which this lower bar is allocated. So that guarantees that the the amount of extra budget you have can't be too much. In particular, the extra budget you have is never more than 1 over LT by the end. All right, so well, actually, let me pause here. Is there any questions about the algorithm or the guarantees? All right. Okay, so we do take our result and we did implement it on a synthetic experiment as well as a food bank data. So the synthetic experiment here, we did both for a single resource and a multiple resource setting, where we take the distribution on the demand to be Poisson. And the blue curve here is from a fixed threshold. It's a naive allocation that always allocates conservatively according to the lower threshold. The yellow, the curve is our algorithm with the LT of t to the minus 1/2. So it allows for its minimum delta MV, but has higher waste. And the green curve is our algorithm with LT being t to the minus 1/3. So it's a slightly higher threshold on the delta MV, but you can see that it gets significantly lower waste. So you can see from the plot on the left is our results for delta MV. Our plot on the right is our result for delta efficiency, and we do verify that it does exhibit this inverse proportionality behavior between these two quantities. So we also did experiments on the food bank data itself, using the historical data on the food bank to then construct a distribution over the demands and simulate it in that way. And we got very similar results in that the fixed threshold has the highest waste, and that our algorithm with this parameter LT allows you to trade off between this delta MV and delta efficiency optimally. So the question of, are we solving a multi-objective optimization? So in fact, our setup is indeed giving guarantees on multiple objectives, in that we give guarantees on delta efficiency and delta NV. And I think what's unique about our setup is that we are able to characterize this full trade-off curve, the full Pareto efficient trade-off curve between these two different objectives that we care about, and showing that our algorithm actually, using this parameter LT, you can choose which point along that curve you want to, I guess, achieve. Okay, so that's the summary of our result, and again, that there's three kind of key pieces to our result. One, this that lower bound, that any algorithm, this first objective, delta MV, we want to minimize, has to be at least 1 over root t. And second of all, the second, I guess, result we show is that delta MV and delta efficiency have to be inversely proportionally related to one another, at least. So that's, again, the two red regions depicted in the plot. And then furthermore, we provide an algorithm that indeed achieves any trade-off along this optimal curve using a very, very simple algorithm with a very simple analysis. And so I think what's really nice about our result is that the results, in fact, do hold with high probability. So this is in contrast to results which guarantee some notion of ex-ante fairness. Ex-ante fairness, or some notion of approximate social welfare optimizing, those guarantees don't really translate in any way to ex-post guarantees, as opposed to our results really show that with high probability, ex-post, you are the allocation we achieve indeed is close to fair in terms of this close to MV-free and close to Pareto efficient. Okay, so that's all I want to share today, and happy to take questions.